Hi everyone, this video is going to cover the second half of chapter 17, and so it is replacing our live lecture for Monday, and thank you again for being understanding. So we talked about that benzene is very stable, and it always comes with the label of being aromatic. Benzene is not the only molecule that comes with that label, so we're going to talk about the rules of what it takes to be aromatic. And the first way we're going to describe it is that it has to follow Huckel's rule, which says that the number of electrons in p orbitals has to be 4n plus 2. So it's kind of a weird way to phrase it. N can be any integer. So if we think about n being 1, then 4 times 1 plus 2 would give us 6. And for benzene, those are the 3 double bonds, 2 electrons each. There's our 6 electrons in p orbitals. Kind of an easier way to think about it, though, is we have to have an odd number of pairs of electrons. The other two rules that have to happen is that we have to have a ring, so you can't be aromatic if it's a chain, and it has to have overlapping p orbitals all the way around the ring. So that means that if we're dealing with a carbon, it has to be sp2 hybridized. Sp would also count, but we're not going to have any sp carbons in a ring. And then if we have a heteroatom, which we'll look at in a few slides here, it needs to have a lone pair that is delocalized. So that means that it can participate. So that whole bullet point there says fully conjugated ring with overlapping p orbitals. So that really just means that all of the atoms can participate in resonance because they have available p orbitals and they have electrons in those p orbitals. The two examples on the bottom don't meet Huckel's rule. So cyclobutadiene has 2 pairs of pi electrons, and cyclooctatetracene has 4 pairs. So 2 and 4 are even numbers, not odd, and so they're not going to count towards being aromatic. A little bit more on our MO diagram. Move this just a little. There we go. This is, again, looking at those MO diagrams, and in this case we're looking at them for those 2 molecules on the last slide that are not aromatic. And what we can see here is for the cyclooctatetracene and the cyclobutadiene, they each have orbitals that are half filled, and those orbitals are laying right on the line between the bonding and the anti-bonding. So notice the label that they're given. They're in this third kind of gray area called non-bonding. And so because they're in this kind of weird category, it's not stable, they're half filled, it means that they're not going to be aromatic. In fact, we actually give them a new label. We label them as being anti-aromatic. And we'll talk more about that definition because we are going to add a third one to that list. We'll talk more about it as we go through the next few slides. The first rule is that we have to have a planar ring. So rule number 1 is we have to have a planar ring. Planar just means flat. So cyclooctatetracene isn't actually flat. It forms kind of this buckled shape, a bowl shape, a boat shape, however you want to think about it. But because of that, the p orbitals are not fully overlapping. These blue ones on this side are going to be too far away from each other, so we don't have a fully conjugated ring of overlapping p orbitals. That's only going to happen if it's planar. So because it's not planar, here's our third label. We're going to call this guy non-aromatic. is a way to figure this out doing what's called frost circles. So frost circles are essentially a watered down version or a simplified version of the MO diagrams, and they're showing us if the orbitals are all in the bonding area. So the green down here, those are bonding MOs, and then the white area are anti-bonding, and then the ones that are right on the line, those are non-bonding. So this is one way to figure it out. We can look at how many carbons we have or how many atoms we have. So notice these go all the way from 4 up to 10, and we can look at how many electrons we have available and fill them in going from lowest energy to highest energy. And if all the electrons are in the bonding, then we know that it is aromatic. These can be confusing though, and it also means you have to memorize all of these diagrams. So we're going to do it a different way. Here's our rules. We have 2 rules. And I can see that I'm going to cut off part of my title here because the bottom part is more important. So there's 2 rules. Rule number 1 says that we need to have an uninterrupted cyclic cloud of pi electrons. So this is really just an expansion of what we talked about a couple slides ago. So let's talk about what that rule means though, an uninterrupted cyclic cloud of pi electrons. So that means it has to be a ring. Every atom must have a p orbital, so that means they all have to be sp2 hybridized, and the molecule must be planar. So that means it has to be flat, and in order to get a flat ring, we have to have 7 or less atoms. If we have 8 or more atoms, it can form that buckled shape, and it won't fulfill rule number 1. Rule number 2 says the pi cloud must contain an odd number of pairs of pi electrons, and so this is following Huckel's rule, so that the total number of electrons is 4n plus 2. We're going to evaluate these rules in order. If a molecule fails rule number 1, we're going to label it as non-aromatic. So this would be something that is a chain, something that contains an sp3 atom, or greater than or equal to 8 atoms. If our molecule fails rule number 2, we're going to label it as anti-aromatic. So that means it has to pass rule number 1. Rule number 2, though, means that it's going to have an even number of pi electrons. And if it passes both rules, then we can label it as aromatic. So let's look at a couple of examples that are over here. We're going to look at that cyclopentadiene row. So starting from left to right, so starting right here, we have a ring, we have an sp3 carbon. So already it's failing rule number 1. Kind of past the first checkbox, it is a ring, but we don't have a uninterrupted cyclic of pi electrons because we have that sp3 carbon. So because it fails that first rule, we're labeling as non-aromatic. The second structure, we have a ring. Every atom is sp2 because when we have that carbocation, it is sp2. We have less than 7 carbon, so it fulfills rule number 1. Rule number 2, the pi cloud must contain an odd number. 1, 2. It has an even number, so we're labeling it as anti-aromatic. And then the last one, we have a ring, we have less than 7 atoms, we have sp2 hybridization. Now, we have this carbanion right here. We got to talk a second about hybridization. hybridization happens in order to make atoms or molecules more stable. And there's a little bit more gray area to it than what we originally had talked about because it's based on stability. If that carbon is hybridized as sp2, we now have 3 pairs of electrons, and we can label this as aromatic. If that's an sp3 carbon, then it gets labeled as non-aromatic because we wouldn't have a full ring of electrons. So because hybridization is rooted in stability, there is actually some wiggle room with it. In terms of overall stability, aromatic compounds are the most stable, and then non-aromatic, and then anti-aromatic. So if we can have an atom hybridized as sp2 in order to ensure it can have that overlap, then that's what's going to happen. So for carbon, we have to have a charge, either plus or minus, and then for our heteroatoms, we can have a lone pair that would be in that p orbital. Let's do a couple examples. So these are all 1, 2, 3, 4, 5, 6, 7. Double check there. These are all cycloheptane. And it's kind of the same idea as what we saw on the last slide. We have a neutral one, we have an anion, and we have a cation. So our first rule, ring less than or equal to 7 carbons, and sp2 hybridized all the way around. So when we look at this first one, we have a ring, we have 7 carbons, but because we have this sp3 carbon, it fails rule number 1. So this is a non-aromatic compound. Compound number 2, we have a ring, we have 7 carbons, we have sp2 carbons all the way around. So then we go on to rule number 2. Rule number 2 says that we need to have an odd number of pi electron pairs. So this one has 1, 2, 3, and there is a lone pair here, 4. Because it has an even number of pairs, we're going to label this one as anti-aromatic, and underneath it I'm just going to put that it had an even number of pairs. And then our last structure, it's a ring, 7 carbons, we have a carbocation, so we can definitely label that as sp2, and 1, 2, 3, this one now has 3 pairs, and so we have an aromatic structure. So what if we throw some heteroatoms into this mix? If they contain nitrogen, oxygen, sometimes sulfur, then we're going to apply the same rules. One of the big things that we have to decide or kind of make judgments on is this bullet point right here. It says we have to decide if the lone pair on that heteroatom is localized or delocalized. So localized essentially means that it belongs to that location. It belongs to that heteroatom. So it stays on the atom. Delocalized means that it can participate in resonance. Another way to think about these is that our delocalized electrons would be in an unhybridized p orbital, and our localized electron would be in a hybridized sp2 orbital. So if we look at our 3 molecules up here, we have pyridine, chiral, furan. You do not need to memorize those names. You will see them often though, so you might memorize them without trying. In pyridine, our nitrogen is sp2 hybridized. So if we think about sp2 hybridized, that means there are 3 sp2 orbitals and then one unhybridized p orbital. So that means there's 4 things that will have electrons in it. So for nitrogen, we have the 2 sigma bonds going to the 2 carbons. We have the lone pair, and then that p orbital, that's going to be the pi bond going to the carbon. So this tells me that the nitrogen's lone pair is localized. It's not participating in aromaticity. Localized. It is an aromatic compound because we do still have 1, 2, 3. We have the 3 pairs of electrons, but that lone pair on that nitrogen is not participating. In the next compound, pyrrole, again, our nitrogen is going to be sp2 hybridized. The difference between pyridine and pyrrole, though, is whether or not it has a double bond. So in pyrrole, it has 3 sigma bonds and a lone pair. These 3 sigma bonds are the sp2 orbitals, and that lone pair is the p orbital. So our lone pair in pyrrole is delocalized. That makes up the 3rd pair. So 1, 2, 3, we have the 3 pairs. I'm going to erase my mess up here and kind of summarize that one a little better. For our pyridine, we have 2 sigma bonds, a lone pair, and a pi bond. The 2 sigma bonds and the lone pair are in sp2 orbitals. The pi bond is in a p. So kind of to make a generalization about this, sigma bonds are always going to be in hybrid orbitals. Pi bonds are always going to be in unhybrid, or we could really just say in p orbitals. And then lone pairs can go either way depending on what's available and what will make something more stable. In our last structure here, furan, in our furan molecule, our oxygen is also sp2 hybridized. It has 2 sigma bonds and 2 lone pairs. So one of those lone pairs is going to be in a hybrid sp2 orbital, and one lone pair is going to be in a p orbital that is delocalized. So 1, 2, 3, it is going to fall into that aromatic category because it does have an odd number of pairs. So when we have more than one pair, we can label them as one of them localized, one of them delocalized. Let's practice this. So we have a few examples here, and we know that oftentimes with heteroatoms we don't draw in their lone pairs, but I think with these it might be best. So I'm going to do it in red just so it stands out. Just going to go down the line here. Okay. So we're going to evaluate these and decide if they are aromatic, non-aromatic, or anti. And remember, rule number 1 is we need a ring, we need less than or equal to 7 carbons, and we need sp2 hybridization. Rule number 2 is that we need an odd number of pairs. And then what we're going to also look at is whether or not the lone pairs on those heteroatoms are participating. So our first compound, we definitely have a ring. We have 6 atoms, so less than 7. Everything is sp2 hybridized, and I know that just by looking at it because everything has a pi bond going to it. So that means it has to fall under that sp2 category. Odd number of pairs, 1, 2, 3. This is aromatic. The lone pairs on those nitrogens, both of them are localized. They are not participating in resonance because they don't have to. The nitrogen has a double bond. When the nitrogen has a double bond, the pi bond going to it is going to be the one in the p orbital, and that lone pair will be localized. So what about in our second structure there? Again, ring, 6 carbons. We have a nitrogen that is sp2 hybridized. It's positively charged because it doesn't have a lone pair. It's bonded to an extra hydrogen. But we still have 3 pairs. So this one is also aromatic. This is actually a pyridine with an extra hydrogen attached. What about the next one? So we have a ring. We have 5 carbons. But that carbon right there is sp3 hybridized. Sometimes we can overlook the carbons if there's a lot of other things going on, so make sure that you're paying attention to the carbons. So we're going to give this the label of non-aromatic because of that sp3 carbon. Looks like our next one might fall into that same problem. So we have a ring, we have 6 atoms, but we have an sp3 carbon. So this is also going to be non-aromatic. And then last, we have a ring, we have 5 atoms. Everybody has a pi bond or a lone pair that can participate. So it looks like it passes rule number 1. We have 1, 2, 3. So we're going to call this aromatic. So let's talk about those lone pairs. We have a lone pair on the nitrogen that is localized. And I know it's localized because that nitrogen already has a pi bond. We have 2 lone pairs on the oxygen. Now because that oxygen is sp2 hybridized, one of them is going to be delocalized. It belongs to that oxygen. It's in an sp2 orbital. The other one we're going to label as localized, and it's in the unhybridized p orbital. So we kind of made a generalization about the nitrogen down here. I'm going to add to that. Let's see. I'm going to do this. Not that. I'm going to write, let's see. Sorry, I'm just trying to decide where I space. I'm going to scoot my screen up. There we go. So for nitrogen, if we have a double bond, then those electrons are going to be delocalized. If we have a nitrogen that has all single bonds and a lone pair, then that lone pair can be I'm sorry, I labeled that first one backwards. Let's try this again. That first lone pair is localized. The second lone pair is delocalized. For oxygen, so if oxygen has a lone pair and a pi bond, so in this case it actually would have to be charged to be in this scenario. But if it was in this scenario, I'm going to move my lone pair. Let's move it to the bottom here. Then that lone pair would be localized because the pi bond is the part that is delocalized. For oxygen, most of the time though, we're going to see it as 2 single bonds. And in that case, 1 lone pair is localized and 1 lone pair is delocalized. This is kind of a good summary of what we would expect to see. If you do see sulfur, it's going to fall into the same category as oxygen because they're in the same family on the periodic table. There might be some other ones that you would see, but they would have to be charged for that to happen. So this is kind of a good roundabout way to summarize them. We can have multiple rings in a system, and have it be aromatic. So these are a couple examples. Naphthalene, anthracene, and penanthracene. So having 2 or 3 benzene rings fused together. So we talked about bridged rings. If two rings share a bond, then they are called fused rings. So just to kind of add to our vocabulary there. And then this also starts us on to our reactions for this chapter. And some of these we've talked about before, but now we're just specifically looking at them for benzylic carbons. So notice the title of this section, Reactions at the Benzylic Position. So we're not reacting the ring itself, we're reacting the benzylic carbon, so the carbon that's attached to the benzene ring. So our first reaction here is an oxidation, and so we are reacting it with sodium dichromate, sulfuric acid, and water. The other option is potassium permanganate, heat, and water, followed by acid. So this one could be written out as KMNO4, water, heat, and then second step is H3O+. The rules for our starting material, so for both of these, is that the benzylic carbon needs a hydrogen. So it can't be quaternary. It has to either be tertiary, secondary, primary, but it has to have a hydrogen attached to it. And when we look and see what we get for the product, that benzylic carbon becomes a carboxylic acid. So regardless of how many other carbons were attached to it, they are broken off and we're left with just that one carbon. And this is reaction number 1, by the way. I don't know if I actually said that. There's 6 reactions in this chapter. Reaction number 2 is a bromination. So we saw this reaction back in our radical chapter. This is chapter 11. So we're using NBS, which is N-bromosuccinimide, and heat. And technically we could use light for this as well, so heat or light. And we're going to add a bromine to that benzylic position. And same thing, same rule as our last one. We need to have a hydrogen. So must have hydrogen at that benzylic position. If you remember the mechanisms for these types of reactions, we're removing a hydrogen and essentially replacing it with that bromine. We saw this set of reagents to react allylic positions. All right, reaction number 3. We can do substitution reactions. So we didn't spend a whole lot of time talking about benzylic positions when we did our SN1 and SN2 reactions, but it occurs. SN1 reactions can happen because it's a very stable carbocation. So in order to do an SN1 reaction, we're going to use a neutral nucleophile. And it's happening because we have a very stable carbocation, even if it's primary. And that's because it has so much resonance to help stabilize it. And the SN2 will happen if we have a negative nucleophile. And this will happen if we have low steric hindrance. So SN2 at this position, we have to have low steric hindrance. So this wouldn't work for tertiary, this would be better for primary or secondary. So it'll get us to the same spot. In this case, we're replacing it with an alcohol, but what pathway we go down can depend on how many substituents there are. So if we can do SN1 and SN2, that means we can do E1 and E2. So again, same reasoning here. We can do the E1 because we're going to have a very stable carbocation, and we can do the E2 because we have a stable transition state. so that benzene provides a lot of stability. This is actually one of the reasons we don't talk about benzene in Chapter 7, because we end up with a huge competition between all four reactions, depending on our nucleophile, our base, and how many substrates are coming off of the carbon in question. So we kind of isolate it to just this chapter. All right, reaction number 5. And 6. So reaction number 5 is a hydrogenation reaction. We know that we can take a alkene and react it with hydrogen, and we'll just get an alkane. Benzene doesn't react as easily though. So we're reacting our benzene, we're reacting it with 3 moles of hydrogen, and then look at this. The nickel is our catalyst. 100 atmospheres, that's just a really high pressure. And then 150 Celsius, so very high heat. So this is not a great reaction because it is producing, or it's requiring so much heat and so much pressure that generally with reactions like that, we're not going to get very good yields. What if we did a reaction just like this? So hydrogen and some platinum catalyst. If we try to do a reaction like that, the only thing that's going to react is that extra alkene. So we do need to have those extra conditions, the high pressure, high temperature, in order to get it to reduce down all the way to that cyclohexane. And then the last reaction on here, and the last reaction in the chapter, is called a Birch reduction. So we're reacting it with sodium, we have some methanol there, we have ammonia, and our benzene reduces down to just having 2 double bonds that are opposites from one another. And this is called the Birch reduction. So we're going to look at the mechanism for this on the next slide. It's a radical-based mechanism. Having just the sodium metal in there gives us a little clue to that. So because it's radical-based, that first step has a lot of arrows, because remember when we draw an arrow, that little fish hook arrow, it's telling us that we're moving just that 1 electron at a time. Sodium has 1 valence electron. So in this first step right here, sodium is giving an electron to one of the benzene carbons, and then as a result, we're splitting this pi bond between those 2 carbons and splitting the next pi bond between the 2 carbons. So what we end up with is a radical anion. The carbon at the top has a pair of electrons, so that's our anion, and the carbon at the bottom has a single electron, that's the radical. So remember, there's also methanol in that solution. So we're going to do a proton transfer. We're going to steal that hydrogen from the methanol. So now our carbon on the top is neutral and happy, but the carbon on the bottom is still a radical. So another sodium, we're going to donate 1 more electron to that carbon. So now that carbon is a full anion, and it's going to go through that proton transfer again so that we can have that carbon on the bottom as a full sp3 neutral carbon. So this is our final product over here. So a little bit more about this one. Specifically, it's regioselectivity. If we have an electron donating group attached to the ring, then when it reduces down, that electron donating group will be on an sp2 carbon. So the way that it looks right here. And if we have an electron withdrawing group attached to the ring, when it reduces down, our electron withdrawing group will be on an sp3 carbon. So this has to do with stabilizing those transition states electrons and whether or not the substituent can help stabilize them as a lone pair, or if it does not help participate. So think about that these two carbons are going to be lone pairs, or have lone pairs at one point. So we would want to have something that could pull the electrons towards the substituent. Whereas if we had something that was electron donating towards the ring, we don't need that. The carbon already has an extra lone pair, so we would want to keep those substituents away from the two carbons that are going to end up with the lone pair. So these two carbons will have the lone pair on them. We want to keep our electron donating substituents away from those two positions. So this is our regioselectivity for this reaction. All right, last couple slides in this chapter are things we've actually already talked about. We have an IR of where we would expect to see aromatic compounds or benzene compounds. So we know that in that 1415 to 1600 area, we're going to see carbon-carbon double bonds. And then in this region up here, we will see overtones that tell us if it's ortho, meta, para, tri-substituted, and so on. And then we have the carbon-hydrogen bonds for an sp2 carbon bonded to a hydrogen. The area over here can also give us information about how it's substituted. So you most likely had to look into this for test number 1 already, but this is just a little bit of a reminder. And then the last thing is the NMR, which again, we have done, and you definitely had a benzene ring or 2 in your test. So we know that the benzene hydrogens are in that 7 area. It can tell us about substitution based off of integration. It can tell us about how it's substituted based off of the patterns we see. And then in the carbon NMR, those benzene carbons are around 100 to 150. And again, how many peaks can tell us about substitution or about symmetry. So kind of went through those last couple slides quickly, but it's because we have talked about that before. So this is it for chapter 17. So I will get this posted for you, and you will be able to watch this on Monday for your lecture time. And thank you guys very much.